Okay, here we are in my EnMath Engineering Math A course, and uh, we're in the module on vector calculus, and this is kind of the last big subject of that, which is surface integrals and more specifically the flux integral. So let me just go through first. This chart kind of tells you in general what it's all about. When we did a work integral, we were integrating over a path, a one-dimensional path, a one-dimensional creature in three-dimensional space. So we were integrating along a path. And the way we went about that was to parameterize that path in terms of a single variable and then integrate over that single variable normally. So we pulled back the path in 3D space into a single dimension and integrated normally. What we're going to do with surface integrals is analogous. A surface is a two-dimensional creature in three-dimensional space. And what we're going to do is pull that back into a flat zone in terms of just two parameters, say u and v. That's what it means to be a surface. It's this position vector. Remember, r is the position vector. U and v in this case are the parameters. You vary these parameters over all their allowable regions, you get a surface of some kind. Just like as you vary this parameter t in the work integral, you got the path. So that's the idea. We're going to try to pull it back into UV's parameter space of two parameters or two variables and integrate as a normal double integral over some region or surface. So let's talk about parameterization a little bit with a couple of examples. Say it's the cylinder described by x squared plus y squared equals a squared, or a cylinder of radius a, and it goes along z from -1 to 1. I think you can imagine that. It's like a can. Up and down in the z direction. One way to parameterize that, remember, we wanted only two variables. Here we had three, x, y, and z. One way to parameterize that is to basically kind of use polar coordinates for the x and y parts. And z can just be z, but I'll call it v. This is all in terms of u and v, where u would go all the way around, so 2 pi. V goes from -1 to 1. So this is a parameterization of this cylinder. Sphere. In XYZ coordinates, it's this thing, a sphere of radius A. One way to parameterize it is kind of like using Latin lawn, where, let's see, U is like longitude and V is like latitude. U would go all the way around 0 to 2 pi. And V would go from -pi/2 up to pi/2. And see, this is only two parameters, u and v, to describe this two-dimensional creature in three-dimensional space. Okay, surface. We're going to need a differential surface. ES. What is that? Here for a better, more complete derivation, as much as it is, email me and ask me for my notes. I'll just kind of walk through the outline of it here. Say here's a sphere described by this position vector over all the allowable u and v, parameterized in u and v. Turns out if you took the derivative of this r with respect to u, It would be a vector in the tangent plane of that surface. You know, if you pick a particular point. Same with the partial derivative of r with respect to v. These two vectors are in the tangent plane. Cross them, we would get the normal vector to the surface at that point. Remember what a normal vector was? We talked about in the previous video. Well, let's scale the r sub u with a little delta u, and scale the r sub v with a little delta v. So that in that tangent plane, we have r sub u times delta u, r sub v times delta v. Let's look at a little parallelogram patch. We had the formula for the area of a parallelogram. It was the cross product. Well, actually, the magnitude of the cross product. And if you shrink that patch down, so where those delta u and delta v became a du dv, or a little dA, where this dA is in the uv plane. And this is the magnitude of the cross product then, of the little differential patch. Because as you go down to the limit, this little patch in the tangent plane is equivalent to the little differential patch on the surface itself. So this is our ds, differential chunk of sphere, of sphere surface, chunk of surface, I should say, not a sphere, chunk of surface. So if you just wanted the surface area, you would just integrate that differential surface area over the entire surface. And what would that mean? This becomes our integrand, integrated over a region in the UV plane. So these R sub u and R sub v's are functions of u and v, and dA is in the UV plane. So we parameterized everything. And if you wanted to integrate the scalar function over its surface, you just insert that function in this integrand, convert it to your parameters u and v, and this is what this would become the integrand. So everything here is how you compute it. We've pulled it back. Everything here is in terms of u and v, two-dimensional space. The good news is we're not going to go really much further with these two guys. We're going to be interested in a third kind of surface integral called flux integrals. Let me try to describe what that is. So here we have our surface again, and it's in a vector field. And you could forget this region R here. We don't need to talk about it just right now. And this is best intuitively understood if you think of this vector field as, say, the velocity of some kind of fluid. We're interested in how much fluid flows through a little differential patch of the surface in some unit of time. Well, let's first look at just a flat patch. Some delta S, patch of area delta S, finite now. How much fluid flows through in a given amount of time? It's the volume in this parallelogram. Parallelepiped, where this F is the velocity of the fluid, say, and this little n is the unit vector that's perpendicular to the patch, normal to the patch. Well, we have a formula for that volume. It's the base times the height. The base is just delta S. The height is the component of F onto N. Talked about that in the previous video as well. And we had a formula for it. Component of f, f1 to n is f dot n divided by the magnitude of n. Well, if we define the n as a unit vector, that magnitude is just 1. So here is the volume in that parallelepiped. Now, when we take the limit, shrink this little area down to a differential area, so it's equivalent to a patch on the surface now. Here is our differential flux. So if we want the total flux through a total surface, we take this integral, f dot n ds over the surface. And let's look at that. Here's the flux integral, f dot n ds over the surface. And the ds we already had. It was this magnitude big N. I think I had that on a previous chart, times dA. I had that on a previous chart. What I mean by big N is this R sub U cross R sub U. That's big sub N. Yeah, here it is. That's big sub N. Oops. So this magnitude of big N dA is the ds. But N, little n, is just the unit vector in the same direction as big N. So that unit vector direction times the magnitude of big N is just big N. So here's what it is. Big N is this, R sub U cross R sub V. You have to convert the vector field from its XYZ components into the parameter space U and V. So here is how we'll compute the flux integral. This is the flux integral, what it means. This is how we'll compute it, at least in the most general case. It turns out we'll have other methods and more in certain situations that we can use that are a bit simpler. We'll get into all. I'll get into, I don't have enough time right now. I'll do an example of this in another video because this is already running 12 minutes or so. Example comes in the next video.